Good afternoon. I'm here to work through the integration by parts 7 ways, the review focused on integration by parts that was completed yesterday and requested by a member of the 2020 BC class probably about 5 days ago, if I have to be honest, maybe a little longer. In this video, I'm going to work through every single problem authentically. I have not made a written solution set yet. I've checked some problems and obviously I've written them carefully, but I'm going to go through every single solution as though I'm seeing it for the first time. In addition, I want to point out that this review is focused on integration by parts, but that only means that every single problem in the set has integration by parts in it. There are many problems that address other concepts and topics and vocabulary, which I think is what actually makes this a really valuable review. You know that the heartstring is integration by parts, but everything else is just calculus tools that could pop up on a future exam. So having said that, let's jump right in and try to work through this efficiently. So problem number 1 I think is the simplest one. It's the only problem that's been written completely on my page since I started writing this out. And it asks us to compute the average value of f of x equals 2x ln of x for values of x between e and e cubed. So now first of all, the average value itself, this is one that you probably remember, at least by Calculus BC. But if not, here it is. The idea behind this expression for the average value is that it finds the definite integral's value, and then it comes up with the height that would be necessary to make a rectangle feature the exact same area as this area under the curve. So that 1 over b minus a is the width to kind of normalize everything else. So in any event, there's our expression. So we want to calculate this specifically for our function here. So obviously the 1 over b minus a part isn't going to be particularly difficult. And writing out the integral is not difficult, but I would say this would be an essential element of this problem if you were doing it. You'd get a point for just setting up the integral, possibly even more than that. Now having said that though, I want to focus our attention on the integral itself, and in fact I'm not even going to think about it as the definite integral. I'm just going to focus on this guy. I'm going to call it little star, and I'm going to try to use integration by parts to work through the integral I'm calling star. So in other words, we've kind of made this into an anti-differentiation problem. So in here, this is an integration by parts problem. I can tell that, or what suggests that, is the presence of this product. It looks like it's possibly something that came from a product rule problem. Beyond that, I'm going to jump in. I use the acronym LIPET myself. Have that little story about telling your dog to fib. So in any event, as I look in here, I notice that we've got a log and we've got a polynomial. This is our log, this is our polynomial. So interestingly enough, although we typically think of polynomials as being our choice for u, in this case ln is going to be our choice for u. So I'm going to go ahead and set this up. I'm going to let u equal the natural log of x. That means dv is going to be 2x dx. And then du, the derivative of ln, will be 1 over x. And v will be the antiderivative of 2x, which is x squared. And I apologize, there should be a dx here as well. So having done this, you can sort of see from setting up the uv vdu kind of stuff here why it is that ln gets that luxury of being chosen as u. The reason is the derivative of natural log transforms it from being transcendental into something rational, something that we can work with and something that will clean up really nicely with the v when we get it in there. So now from here, if we're using integration by parts, it's worth reminding you that the expression in its simplest form is uv minus the integral of v du. So that's what we're going to be setting up here. So in other words, if we look at our little table here, uv is going to be x squared natural log of x, and then minus the integral of v du. That's going to be the piece right over here. So minus v du is going to be the integral of x squared times 1 over x dx. And having done that, we can clean this up a little bit because that x squared times 1 over x dx cleans up really nicely. We get minus the integral of x dx. And that means that we can evaluate this really quickly. We get x squared ln of x minus 1/2 x squared. And then of course plus c, since we did get an indefinite integral. And so there is our antiderivative. So that's what we're going to be using with the fundamental theorem. Well, not the plus c, but everything else that's there. So that completes my work on figuring out an expression to help me evaluate star. So having done that, I'm going to pull this up to the top and go ahead and proceed forward. So, and in truth, I probably shouldn't have put that bar there, but whatever. So this is equal to 1 over e cubed minus e. As far as the expression here, we just saw that it's going to be x squared ln of x minus 1/2 x squared. And I could definitely factor out a GCF of 1/2 x squared if I wanted to. It's tempting to do that. Like, maybe I'll do that in a second. You know what? In fact, I'm going to go ahead and do that. Like, let's do that before we go forward. I will be evaluating this in a second. So if I go to clean that up a little bit, and again, it's just my personal choice. I just prefer to do this. So I'm going to factor out a GCF of 1/2 x squared, just because I like getting that fraction out of the way too. That leaves me 2 ln of x on the inside and a -1. And then this will be what we evaluate from e to e cubed. So there's kind of our starting spot. So having done this, like, we're almost ready to, or almost to a point where we could stop. So, well, we'll get there. So we have 1 over e cubed minus e. In here, if we plug in e cubed, we're going to have 1/2, and e cubed squared, to plug that in here, is going to be e to the 6th. And then we'll have 2 ln of e cubed minus 1. We'll evaluate it in a second. On the second one, we'll have 1/2 of e squared, because we're just plugging e in for x. And then we'll have 2 ln of e minus 1. And that's going to be our entire expression. So we've got a little ways to go before we finish this up. As far as things that we can clean up here, we have 1/2 e to the 6th. ln of e cubed is 3, so this is 6 minus 1, or 5. And then the next one, we have 1/2 e squared. We can actually pull out a GCF here in just a second and see if we can clean it up a little more. ln of e is 1, so this is 2 minus 1, which is just 1. So actually, we don't even really need to worry about that, but I've got more steps to clean up, so I'll just let it be. As far as things that we can evaluate here or pull out as GCFs, I notice that I can pull out an e squared, so I'm going to go ahead and do that. In fact, I'll pull out a 1/2 e squared, so this will become e squared, and then the 1/2 will bring a 2 out there. But I notice in my little average value, like 1 over the width multiplier, I have a GCF in itself, so I'll pull out an e right there. It'll leave me e squared minus 1. And then on the inside here, since we pulled out the 1/2 and the e squared, that's going to leave me with 5e to the 4th, and then minus 1. And obviously many of these answers, in fact, probably as soon as we got here, you could have technically stopped. This would have been a great stopping point, but I don't want to stop. I can do this. So as far as cleaning up what's left here with this mess, we can divide out one of those e's, and that's going to give me the answer that I'd consider probably the best version. We'll have e times 5e to the 4th minus 1. And then in the denominator, we'll have 2 quantity e squared minus 1. So there is what I'm going to term our final answer, which solves this problem nicely for us. So you can see in this average value, the big challenge probably came from just the fundamental theorem part. Like, there was a big challenge that came from simplifying, but in here, the important structures to remember, I'll highlight them here in green or underline them in green. Remembering that expression, uv minus the integral of v du, that's instant communication that you know integration by parts. Knowing or recalling LIPET, so that way you can make a good sound choice of your u and dv. And then, of course, executing your antiderivative and keeping your work organized. Like, I, again, use this system of like star to kind of do these mathematical soliloquies. How you do it is your call, but I think this is the easiest way to avoid a linkage error somewhere and make sure that I don't actually say something's equal to something that it's not truly equivalent to. But in any event, there's our answer. I feel good about my work. Problem number 2 then asks us again to use integration by parts, but in this case it comes in the context of a volume of a solid of revolution. So in this case, we're told at the beginning to let R be the region bounded by the graph of e to the negative x over 3. So if we're trying to picture what that looks like, it gets a little bit smaller as we go forward because we got that negative exponent. It says between that function and the x-axis for x values in the interval from 0 to 3. So giving us a quick little rundown of what our region will look like. Basically, if we plug in 0, we get e to the 0, which is 1. So we've got something along this line. Goes from 0 to 3, so there is our region itself. And again, we're not drawing the solid right now, we're just trying to sketch what the region's going to look like. And we did that. Let's do this. Boom. Okay. So in addition to that, of course, the regions are revolved about the vertical line x equals -1. So -1 would be somewhere right here, and that would create our region. Nice reflection over here. And if you were counting at home, that'd be go from -2 to -5, by the way. Not that that matters, I'm just pointing it out. And having done this, this sets up everything that we need to. We want to compute the volume of this solid. So a couple things to point out. First, it is possible to do this with washers. It absolutely is possible to do this with washers, but it's going to be fairly challenging because you're going to have to split this up into two integrals. So I'm choosing not to do this in terms of washers and to turn everything to y. That just looks like that might be difficult, and truthfully I haven't done the problem that way and I didn't prepare for it. So what I'm going to do instead is I'm going to use cylinders. My thinking being top minus bottom here, here's our actual region. Top minus bottom never changes here. No matter where we look, we're going from the exponential to the x-axis. So I'm going to pick a spot and I'm going to set up my little cylinder. And again, what's nice about the cylinder method is, of course, you don't have to change variables. We get to keep everything in terms of x. So it's worth reminding ourselves, though, what is the formula for the cylinder method integral? So in our case, it's going to be 2 pi times the integral of r times h. And then, of course, dx for us because we're going vertical cylinders. So setting all that up is going to be our focus here, at the very beginning at least. So, of course, the 2 pi gets to stick around. That's not going to be bad. And since we're in terms of x, we can definitely go from x equals 0 to x equals 3. That was a nice twist. They gave us that. Our radius is going to require a little bit of work, though. Our height, on the other hand, isn't going to be bad. This is our height. Our height is just top minus bottom. So if height is top minus bottom, pretty standard thing to calculate, we can see that the bottom is the x-axis and the top is e to the negative x over 3. So our second portion here, our second factor in the integrand, will just be this. So that works out really nicely. The bigger issue, though, here as we look, is that, of course, our radius needs to be taken care of. And I'll use a different color for the radius as well. I'll use it in green. So our radius is trying to describe this length, which is moving side by side. In our R case, we're going to do right minus left. And again, by the way, if you're looking at this going, well, I don't need to do that, I can see this really fast. That's fine. I'm just trying to explain it and give full context where I can. So right minus left, right is going to be our x value, and our left is going to be -1, which means our radius factor is going to be x plus 1. So we're going to go ahead and plug in x plus 1 there, and we're ready to work through this problem. Now, I will say that there is one way that you could attempt this problem that I wouldn't recommend, and I'll tell you why. Some people would look at this and they'd distribute this through and then separate it out into two separate integrals. The reason I'm going to advise against that is because you still have to do integration by parts, but then there's also this second integral that's really easy to lose track of when you've got all this other stuff going on. So instead, I'm just going to work my integration by parts magic right here. So in looking at this guy, I need to choose my u and dv. So in making my choices here, I recognize, of course, that there's this e, and e goes on a lot. So as I make my choice of LiPed, it's going to be pretty obvious that we want to make that e portion our dv. And in fact, notice it does match. We have polynomial and exponential. It's gym class in elementary school. It's PE. But in here, we want to, of course, we know exponential functions are easy to integrate, so it's simple for us to choose that way anyway. So our u is going to be x plus 1. Our dv is going to be e to the negative x over 3. And then as far as du, we're going to differentiate going downward. So the derivative of x plus 1 is 1, and the derivative of 1 is 0. So remember, we can put that plus, the minus, and the plus here. So again, I'm using the tic-tac-toe kind of tabular method for integration of parts here, just because I typically do with exponential. This would work great with uv minus the integral of v du as well. As far as the antiderivative of, let's make sure I do this carefully. As far as the antiderivative of this guy, like if you're kind of thinking it through, it might be worth doing your own little soliloquy over here. That's the same thing as e to the negative 1/3 x. That's going to be a u substitution problem, unless you're comfortable doing it on your own right off the bat. That will give us du equals negative 1/3 dx, or negative 3 du equals dx. And the reason that's helpful is it tells us right here that this is going to be negative 3 e to the negative x over 3. And if you ever get one of these expressions, you're like, wait, is that right? Just take its derivative. In this case, you'll see you do get what we're looking for. And then from here, we'd do it again the same way, which means we'd have another factor of negative 3, which would give us 9e to the negative x over 3. So from here, that gives us all the ingredients that are really necessary for us. I'm just going to make one little move here. I'm going to move lipet over so that way I have room to work. My apologies. It's clear where our progress was. So in tic-tac-toe, recall we multiply diagonally. And of course, this nice thing is that last row would be the integral, but because there's a 0, we don't need it at all. So we're going to have two terms in our integration by parts. So being careful here to make sure I'm doing this correctly linkage-wise, we've just evaluated the antiderivative, or we're going to have an expression for the antiderivative here. So our antiderivative is going to be negative 3e to the negative x over 3 times x plus 1, and then minus 9e to the negative x over 3. So honestly, that's not that bad. That was a pretty clean integration by parts problem. The only thing we're missing here is we need to evaluate from 0 to 3. So now that we've reached this point, it's just a matter of us, putting everything through and cleaning it all up. Like, it may not come out to be perfect, but, we'll check the answer afterwards. So in here, we're going to keep that 2 pi out in front. I'm going to be really aggressive keeping it there. We're going to need a little bit of room here, by the way, to evaluate this. We're going to get now negative 3e to the negative 3 over 3. That's me evaluating right there. So negative 3e to the negative 1. And then we'll be multiplying times 4. On the second term, we're going to have minus 9e to the negative 1. So that cleans up our first term. So in order to make sure that I don't mess this up, I'm going to add a second parenthesis here. It's one of my favorite tricks, by the way. Sometimes I kind of catch myself this way. On the next one, we're going to plug in 0. It's going to be negative 3e to the 0 times 0 plus 1. And then we'll have minus 9e to the 0. So that second term is deceptively clean for us to evaluate. But, again, as a reminder, by the way, AP exam, that would be your answer. You could just stop right there. We've got everything evaluated. It's good to go. No harm in stopping there if you don't want to. It's not who I am, and I'm not taking an AP test right now. So I'll keep going. So what is this going to give me? It looks like we're going to have negative 12 over e minus 9 over e. So that's kind of nice. Those will combine really nicely. I'm cool with that. On the next one, we'll have minus, and then we'll have minus 3 minus 9. Okay. So taking a stab at this guy, we'll have 2 pi times negative 21 over e. And then it looks like plus 12. And then this is pretty good. Like, this is a pretty good final answer. But again, I'm just not satisfied yet. So I'm going to get a common denominator here. Again, you may disagree. I'm going to multiply up and down by e. That's going to give me now 2 pi on the outside. Actually, I'll write it a little further to the left. That'll give me now 2 pi times 12e minus 21 divided by e. And I could stop right there, but I'm not, because I see a possibility here. If I multiply 2 pi through, it's going to give me 24 pi times e minus 42 pi. And then, of course, the whole thing is divided by e. So there is my numeric answer. My numeric answer. It's my number answer. So I believe that is actually our volume in this case. But you know what? Let's take a stab at, let's look at Desmos and see if we did evaluate it correctly. So let's see here. So first, I'm going to get frustrated that the screen won't cooperate with me. There we go. You can notice, by the way, that my answer to the first one was indeed correct. I'm very proud of myself. Because again, I don't have a key here, so I don't really know what's happening. I don't know what to expect. So 0 to 3. In here we'll have x plus 1 times e to the negative x over 3 dx. Okay, it gives us a value of 26.85767. Okay, cross your fingers for me that we're okay here. I'll be dividing by e. It's going to be 24 pi e minus 42 pi. Oh, heck yes. Whew. Okay. 2 for 2. Glad I'm checking myself. That would be embarrassing. I don't want to upload an incorrect video. But in any event, there we go. So what did we get here? We got some great integration by parts. Actually, probably one of the simpler integration by parts problems that we're going to run into. But more than that, we got to review all sorts of volume stuff. We got to evaluate a tricky function with the fundamental theorem. Just lots of really good stuff here. Problem number 3 then. I'll probably do this one and then take a short break. Brings the rectilinear motion problem in. So we've got a particle moving along the x-axis such that its acceleration, let me go ahead and underline that really fast. It's important for me to note, such that its acceleration is given by v prime, interesting notation choice, 3t squared cosine of 2t, so looks like integration by parts, surprise. If the particle has velocity 10 at t equals pi over 2, who's got that clock? What was the exact initial velocity of the particle? And by the way, in here it's worth pointing out, since sometimes it's not always clear, initial velocity in our situation here can be assumed to be 0 because of the fact that we're told that t is greater than or equal to 0. So there's at least some conclusion in there. Okay, let's take a look at what we have going on here. So first of all, we have talk about acceleration and talk about velocity. So here's kind of my thought. Like, here's what I'm thinking will outline this problem for us. The integral of v prime of t dt is going, evaluated from a to b, is going to be equal to v of b minus v of a. So in a sense, what we're using in this problem is we're using the Franklin Theater Company, or better yet, we're using the fundamental theorem of calculus. Love watching a good play, but probably less helpful in evaluating integration by parts problems. So thinking this through, it looks like it's a fundamental theorem of calculus problem. Only difference is we're not necessarily going to use a calculator. Obviously, you can use a calculator and it totally nerfs this problem, but if you came here to practice integration by parts, my thought is you don't want to just punch the question into a calculator and get an answer. So hopefully not. So in here, as far as pieces, if we're going to try to evaluate this, we'll have the integral, and I'm going to go ahead and say that it's going to run from 0 to pi over 2. That seems like a fair bet since those are the two t values we have. We have this guy and we have this guy. V prime was told to us as 3t squared cosine of 2t dt. And then we know that the velocity is 10 at t equals pi, or at t equals pi over 2. So that means this is going to be 10 minus v of 0. And we're trying to evaluate v of 0. So now the way we're going to approach this is naturally like we've done before, by evaluating this integral and focusing on that integral first and foremost. So let's go ahead and focus on it. So once more, as I've done a few times, hopefully LiPet's in your head already, but I'm going to choose to use LiPet. So I need to make choices for my u and my dv. And then I'm going to use tic-tac-toe simply because I see that 3t squared, and I know that's going to differentiate to 0 pretty quickly. So the tic-tac-toe table seems like a smart choice because it allows me to avoid having to do multiple iterations of integration by parts and having negative signs floating around. Tic-tac-toe, awesome method. I mean, truthfully, I should be pointing out, by the way, that anytime you see integration by parts, especially on the AP exam, you should probably just write this once. But setting that aside, I'm going to use the tic-tac-toe strategy. It's going to get me there fastest. So once more, we look at the particular choices we have. We have a polynomial and a trig function. So physical therapy, PT, we're going to choose the polynomial for u, as we expected. 3t squared, 6t, 6, 0. We'll go plus, minus, plus, and then the sign doesn't really matter on 0, but I like to be complete. As far as dv, we're going to have cosine of 2t. I will admit this is usually the spot where mistakes happen. It's easy to have happen. So I'm going to think about it in terms of differentiation. What function has derivative cosine? That would be positive sine. So this will be sine of 2t, but because of that 2, we need a 1/2 to counteract the chain rule's multiplication by 2. Then we go one more step backward. We'll get negative 1/4 cosine of 2t, and then we'll get negative 1/8 sine of 2t. You can see I'm almost running out of space, but we're going to make this work. So from here, tic-tac-toe. It's not my best arrow or best line in the middle. Let me redraw that puppy. There we go. So from here, I'm going to go ahead and try to link this. I think I can do this. I think I can do it as a linkage. So in here, in our antiderivative, we're going to have, it looks like 3t squared, or 3/2 t squared, sine of 2t. Then we're going to have minus a negative, so plus 6 over 4 is going to be 3 over 2t cosine of 2t. Then that last one is going to be minus 6 over 8, which is minus 3/4 sine of 2t. And then that is going to be evaluated from 0 to pi over 2. And this looks like it's going to be a lot, but I'm really hopeful that it's going to be okay, simply because plugging in pi over 2 when we have a 2 in there is going to give us pi. And sine and cosine of pi tend to be pretty easy to work with. But we'll be careful. So let's see what happens here. So if we plug in pi over 2 on the first term, we're going to get 3 over 2 times pi over 2 squared, not thrilled, sine of 2 pi over 2, which is sine of pi. That's 0. On the next one, we're going to get, it looks like 3 pi over 4 from multiplying 3 over 2 times pi over 2. This will then be cosine of pi, which is not trivial, but we'll get there. And then on this last one, we'll have minus 3/4 sine of pi, which is 0 also. Good stuff. On our next term, when we plug in 0, don't just assume it's 0 because it isn't. If we plug in 0, we'll get 0 for the first term because of the t. We'll get 0 for the second term because of the t. And we'll get 0 for the third term because of the t. Ha, got you. I got you to stick with it. It was indeed 0 as it turned out this time. So it's really all about that first term. So that's going to be, it looks like sine, oh, we already said this, didn't we? We said sine of pi was 0, so those go away. This is going to be 3 pi over 4 times negative 1, which is negative 3 pi over 4. And that's a lot of work to get there, but it's actually huge because that's our definite integral's value. Now we just need to solve what that makes or forces v of 0 to be equal to. So moving some stuff around, we'll get that v of 0 is equal to 10 plus 3 pi over 4. That is a great final answer, but I want to do a little bit better. If I multiply up and down, I'll do this in green, multiply up and down by 4, we will get, you can see I jumped the gun a little bit there, 3 pi plus 40 divided by 4. So it is my belief that 3 pi plus 40 over 4 is going to be our correct answer. Once again, let me go ask my good friends at Desmos.com whether I did it correctly. And see how little I trust myself on these. Okay, so first of all, let's see what the answer's equivalent to. That's 3 pi plus 40. 12.356 is what we're shooting for. Cool, cool, cool. There's our integral. Go from 0 to pi over 2. This will be 3t squared times the cosine of 2t dt. And they tell us that the answer is negative 2.356. So your mind starts to go, oh no, we got it wrong. But we didn't. We didn't. The definite integral is definitely equal to that. Remember that we have the definite integral equal to 10 minus v of 0. So v of 0 would actually be 10 minus that answer, which matches perfectly. So a cool 3 for 3. We're getting somewhere on these integration by parts problems. So let's try my luck and do one more before I take a short break. Question number 4. Yes, I think I worked out this one pretty carefully when I was writing it out to make sure it would work, so we'll see if it cooperates. So it says evaluate the improper integral, that one, or show that it diverges. Okay, sounds good. So in here, as far as vocabulary that's really essential when you kick things off here, the most important thing I can say right off the bat is you're not necessarily going to be told in a standard problem that it's an improper integral, but if you are, or if you happen to see any sort of infinities in those limits of integration, your first rule of thumb should be to set up the limit. Remember, definite integrals are only defined for finite intervals. Definite integrals only defined for finite intervals. So we need to make this a definite integral over a finite interval. So we say it's the interval from a to 3 pi over 4 of e to the 4x sine of x dx. And now right at this moment, you probably think to yourself, okay, we got to start carrying this limit a bunch of times. Once again, you're going to see me do this a lot. I'm going to focus my attention on the integration by parts by doing a quick little aside. Mathematically, if you decide to study math, like they often call these kind of mini proofs within a proof a lemma. This isn't a lemma because it's just us doing a computation, but at the same time, that's kind of the organizational strategy I'm using here. You just kind of go off to the side, work through something else, and then come right back to the traditional story. So in here, I just want to evaluate the integral of e to the 4x sine of x dx. So in order to do this, this looks like integration by parts. It is. We're also on an assignment called integration by parts 7 ways, so we're just going to attempt. So once more, I'm going to choose my u and dv. In here, this is a classic LIPET situation. They all are. Integration by parts kind of fits that way. As far as my function types, I see an exponential and a trig. So interestingly enough, I'm going to let u equal e to the 4x. The derivative is going to be 4e to the 4x. And we could obviously keep going, but I'm not sure how far we're going to need to go. So for now, we'll do the dv. So we have sine of x. The function whose derivative is positive sine is negative cosine of x. And then if we wanted to go a little bit further, we could. But for the moment, let's just stick here. So as far as the way we want to evaluate this particular integration by parts problem, one that's truthfully probably unlikely to show up on the AP exam, particularly in this short format, but definitely is integration by parts, so I wanted to honor that. As you go to attack this thing, something to note is that if you write out those first two terms, like everything goes fine, but more importantly, if you do the uv minus the integral of v du, you'll notice that the integral you get down here just requires integration by parts again. This expression, I'm going to erase this after, but this expression would be negative e to the 4x cosine of x, and then minus the negative integral of 4e to the 4x cosine of x. So basically, our goal in this particular problem is to be able to rewrite this as a multiple of our original integral, and then just kind of solve around the edges. But unfortunately, because we have e to the 4x cosine of x and not sine, we can't actually stop right there. So instead, what that's telling us we need to do is we need to take this one more step. We need to go another line in our integration by parts. So if we do that, we'll have 16e to the 4x. The function whose derivative is negative cosine is naturally negative sine. And then now we've got everything set up. So we've got those two pieces ready to go. And in fact, I'm going to go ahead and write them out. I'm going to do that. Excuse me. I'm going to go ahead and just do this down below. I think we'll be okay evaluating up there. So if we do this, looking at our work, we're going to get, it looks like negative e to the 4x cosine of x. We're going to get plus 4 e to the 4x sine of x. And then on our last term, this is the one that people tend to get caught up on, we've got this last line that represents the integral of v du. Combining the signs and everything, we're going to get minus 16, I'm just pulling that GCF, or that scalar out in front, 16 times the integral of e to the 4x sine of x. And now before you pause and go, wait, that didn't answer the question, go back to our original problem, or at least the original antiderivative we were trying to solve right here. That is what this entire thing is equal to. These two sides are equivalent. We've just happened to end up with a multiple of what we're trying to solve for on the left side. So what I'm going to do is I'm going to add 17 of those integrals. I'm just going to put dot dot dots there for time-saving measures. We're going to add that to both sides. When we do, we're going to get a new expression. On the right side, we're going to get 17 times the integral of e to the 4x sine of x dx, which isn't quite what we wanted, but it's getting there. And on the right side, I'm going to pull out a couple GCFs as I do this. You're going to get e to the 4x pulled out as a GCF, and then 4 sine of x minus cosine of x. So there's our work, there's our stuff. I mean, technically there should be a plus c here, but I'm not worried too much about it right now. We're just kind of doing some work off to the side. Last thing I need to do is I need to divide both sides by 17, and I can do that pretty fast. So having done so, we now have our expression for the antiderivative of e to the 4x sine of x. It just required us to do that multiple of the original integral strategy. Now that we have it, though, we can absolutely return back to our original problem, where I'm going to be a good soldier here, and I'm going to include the limit as a goes to negative infinity every single time. Try to make sure. Okay. So in here, as far as what we're evaluating, we have our antiderivative, and I'm going to go ahead and, I'm going to try to save myself a little bit of time here. I just don't think that rewriting that expression is going to be my favorite use of time, so forgive me for cutting that little corner for us. So there's our expression. Of course, there's no a here because we're going to use the fundamental theorem of calculus. So going in, I'm still going to have an a in my expression, so I'm going to keep the limit there. It should be there the whole time. When we plug in the 3 pi over 4 now, it's kind of our first challenge, we're going to have, it looks like e to the 3 pi over 17. Then we'll have 4 sine of 3 pi over 4 minus cosine of 3 pi over 4. And yeah, that's going to require us to do a little bit of work, so we'll deal with that in a second. When we plug in a, it's going to be e to the 4a over 17, and then 4 sine of a minus cosine of a. So as you look at this, you might start to get the feeling like, uh-oh, this isn't going where we want it to. This is going to be a problem. We've got sine of infinity and negative infinity and cosine of negative infinity. The truth is, yes, those things are happening, but the important thing is going to be the controlling term. So let's plug in what we got here and try to clean this up. So I'm going to now drop the limit because I'm going to plug in negative infinity. It doesn't really affect our first term. We'll have e to the 3 pi over 17. What an awkward expression. 4 sine of 3 pi over 4. If you need to think about that, you can, but 3 pi over 4 is a 45-degree reference angle in quadrant 2. So quick little thinking. You are here. Let's say you already used star. But you're going to be over in this quadrant. So sine's going to be positive root 2 over 2, which is going to give us 4 root 2 over 2. And then cosine of 3 pi over 4 is going to be negative root 2 over 2, which will make this plus root 2 over 2. And actually, it turns out nicely to have left that as 4 root 2 over 2. We can combine like terms really easy. On the next one, we're going to get e to the negative infinity over 17 times 4 sine of negative infinity minus cosine of negative infinity. Now, as I said, this isn't ideal. This isn't our favorite expression in the world, but the nice thing here comes from our first term. If we rewrite that, I put an equal sign, I apologize. If I rewrite this expression with no negative exponent, we're going to end up with, and again, this isn't ideal to erase work we did, but playing the same line, we'll get 1 over 17 e to the infinity. And the important thing to note here is that 1 over e to the infinity is the same thing as 1 over infinity, which makes this 0. So in fact, this first piece becomes 0, which makes this entire thing 0. That means the answer to our question is going to be e to the 3 pi over 17 times 5 root 2 over 2, which cleans up into 5 e to the 3 pi root 2 over 34. So there is my numeric answer. If I wanted to be most clear, I would say that it converges to that value. So I'm just going to be lazy. No, I won't. Yeah, I'm going to be lazy. I knew this converges to the integral. I should say the integral's name, or by name, but I'm choosing not to. Oh, are you kidding me? It wants to bring all that along for the ride? Why does this not ever just follow what I want? Whatever. So there is, it converges to that value, and then that is the best explanation we could have, other than, being formal and actually stating the integral itself. So I feel like we found what we were looking for, but again, as usual, sometimes I feel like I should probably check my answer. So let me go do that. Now, Desmos isn't our ideal location to check this particular integral, so instead I'm going to visit my friends at Wolfram Alpha. So I want to do the integral from negative infinity to, we had 3 pi over 4 of, and then our expression I think was e to the 4x sine of it, yeah, of e to the 4x, and then times the sine of x. Well, let's see what happens. Does it give us this value? Please give us this value. Oh, it says it's 2570. So wait, 5e. Shoot, it looks different. 5e to the 3 pi over 17 root 2. Oh, they just didn't rationalize. Okay, yeah, we should be good. So everything looks good. Let me make one more confirmation just to make sure. So 2577.1. So if we do this, 34, 5e to the 3 pi square root of 2, 2577.1. Yes, we got it. I'm 4 for 4. So halfway or over halfway through, feeling pretty solid about integration by parts, at least 4 ways. The next question we're going to address is question number 5. And question number 5 is a function presented numerically, or features a function presented numerically. So we have that table of values over there with values of f and f prime. And then we're told some information about a particular definite integral. And as I look at that definite integral, which has an integrand of 4x f prime of x, different from what the original posted assignment featured. It was a mistake originally. As I look at that, I go, oh, okay, that looks like we're going to probably need to use integration by parts. The weird thing about this question, other than all the things we've pointed out already, though, is since we're told what that definite integral is equal to, we're then asked to find some other definite integral that doesn't look like integration by parts at all. So it's going to be sort of an unsettling problem, although it will resemble some of the work we did in our first practice test this previous Saturday in 2020. So in looking at this expression, I'm going to focus all my attention on this portion, because that's the part that has the integration by parts in it. So I want to try to figure out what's going on with the integral of 4x f prime of x dx. And see if I can find some way to bring in this expression. So going in here, I can imagine that for some people this would be somewhat unsettling, because when you go to make your LIPET choice, we don't know anything about f of x to be able to decide what type of function it is. Is f prime a trig function? Is it exponential? Is it a natural log? We don't know. And for that reason, instead, we need to think about a good choice for making we need to think about which one's going to be appropriate for u and dv. If, for instance, we decide to make f prime of x our u, then we would next compute du, which should be f double prime of x. Now, there's nothing wrong with f double prime of x, except we don't know anything about f double prime of x. Our table only features a row for f and a row for f prime. So that tells me that this is not an ideal choice. And that means that we're going to be forced into letting f prime of x be equal to dv. And of course that should work a little bit better because anti-differentiating, the function whose derivative is f prime, would be f of x. So this looks like a much more promising move. So let's follow that through. That forces u to be 4x. That means du would be 4, and then we differentiate one more row to get 0. There's a problem though. When we go and set up the plus minus plus stuff and we start to tic-tac-toe, you'll notice right away what I'm already noticing, which is what? There's nothing there. There's nothing happening. There's no function there. What is this? Do we write it as the negative first derivative of f? And the answer is, yeah, kind of. That -1 notation is sort of inverse notation. What function has derivative f? Well, that'd be whatever function is represented by the integral of f. And there you can sort of see where we might be able to kind of hook in this expression. Looks like we're going to end up with needing this expression here, the integral of f of x. So having done so, let's see if we can't bring this information together a little bit. So I'm going to move LIPET over to, so I'm just going to move this up. Should have thought about that before. I've been having trouble placing my LIPET. Okay, I'm not going to LIPET. I'm having trouble placing it. There we go. So given this information, based on what we've just done, it looks like our expression here is going to be 4x f of x, and then minus 4 times the integral of f of x dx. So that is kind of our that is our indefinite integral expression. The problem is, though, of course, we are dealing with a definite integral. So we're going to need to rewrite this in a slightly different way. So I'm going to add some stuff here. So we're going from -2 to 1. So first, looking at our expression here for the antiderivative, I'm just going to do it this way. Pardon me. I just need to add a little bit of room. So we're trying to evaluate this definite integral. Well, naturally, we're going to need to use the fundamental theorem of calculus. That will take care of the first portion of our antiderivative. For our second one, though, we have this indefinite integral here, but because we're dealing with a definite integral, it's just as simple to go ahead and just give it that expression as well. That way we've committed no linkage errors here, and we're ready to evaluate each portion separately. We know we can use the fundamental theorem of calculus on the first part, and for the second part, it is an integral, so we'll just make it a definite integral. That should definitely help us out. So as far as the evaluation portion goes, we get 4 times 1 times f of 1, minus 4 times -2 times f of -2, and then still, minus 4 times that integral that we're interested in. So cleaning this up one more line, just to kind of get everything settled here, I'll move it even over a little bit to the side. That's going to give us 4f of 1, which is going to be 4 times 4, and then minus a -8 times f of -2, which is 5, and then minus this integral thing that we're going to have to deal with. And And that means 16 plus 40 is 56. So we have 56 minus 4 times that integral we're looking for. And that's our definite integral's value. And at first you kind of go, okay, cool, we're done, right? Like, what do we have left? Well, the answer is, we were told that that definite integral was equal to 50. Like, we know the value of that integral. So we can go ahead and say that this entire expression is equal to 50. In fact, all of these were equal to 50. We just didn't really dig into that for the moment. So we've got a little bit of work to do here, but this isn't going to be too bad. This equation is eminently solvable. So the way I'm going to do this, I'm going to make a couple algebraic steps at once. I'm going to subtract 50 from both sides and add 4 times that integral to both sides. That's going to give me 6 equals 4 times the integral from -2 to 1 of f of x dx. After that, if we divide both sides by 4, we're going to get that 3 over 2 is equal to the integral from -2 to 1 of f of x dx. And guess what? We solved the problem. There's our answer. Turns out that definite integral has to be 3 over 2 in order for that original problem's value, or the original definite integral, to be equal to 50. So again, lots of little interesting places where things could kind of go awry in problem number 5, but overall not a bad problem. Interestingly enough, though, the first problem that I'm not able to check on Desmos or Wolfram alpha, so that's too bad. Question number 6 is the next problem we're going to run into. In this case, it looks like we've got a separation of variables problem. If you're wondering how I knew, it says separation of variables. It always helps a little bit. So in here, we're talking about a particular solution to a differential equation. So that's kind of an interesting setup. So I'm going to go ahead and write this out. So our differential equation, at first, I'm not sure. Is it going to require integration by parts? Maybe the problem writer messed this one up. I don't know, we'll find out. So we got that. We also have our initial condition. It looks like we're passing through the point -1, comma, e to the 6th minus 2. Okay, we'll see what happens. Okay, so I think everything's set up here. There's nothing really unstandard. Found by separation of variables, find an expression for f of x. Yeah, we're solving this by separation of variables. So let's jump in and do that. So I'm going to first divide both sides, or multiply both sides by 1 over y plus 2. It'll give me 1 over y plus 2 dy is equal to 4 arctangent of x. And again, as you're looking at this at first, you're probably thinking no, there's no integration by parts here. It just got a single function. And starting off from the left side, this doesn't necessarily push us in that direction either. We get the natural log of the absolute value of y plus 2. On the right side, though, that's where things start to happen. So this right side, we have 4 arctangent. We know what the derivative of arctangent is, but we don't know what the integral of arctangent is. So it's at this point that I'll point out what we need is really to deal with another one of those little mathematical soliloquies. So I'm going to go work through star here. Let's see. I'm going to go ahead and do it off on the side here. I think I can make it in time or in space. So if we're going to attack the integral of 4 arctangent of x, we need to make some choices about u and du. So thinking about LIPET here for the first time, or once again for the first time in this problem, we have an inverse trig function, and we have a polynomial. Now you might not think of it as a polynomial, but 4 is really just a polynomial. So basically we have our choices. That means when we set up our work, and again I'm going to use uv minus the integral of v du, something I know I should have said on every single page, but I've forgotten a couple times. I'm going to let u equal the inverse trig function, since it came earlier in that LIPET acronym. Means we're going to have arctangent of x as our u, and that's going to leave dv to be 4 dx. When we go to calculate the next line, the derivative of arctangent is one that's probably in your head by now. It becomes a rational function, 1 over 1 plus x squared. We'll put the dx in there for completion. That will also leave us v equal to the antiderivative of 4, which is 4x. So we now have everything set up for us to write out what uv minus the integral of v du is. So writing that out, uv minus the integral of v du, that's going to be equal to uv, so 4x. I'm going to write it as tangent inverse of x for space reasons, minus the integral of v du. So minus the integral of 4x over 1 plus x squared. And then dx, of course. So writing all that stuff out, everything looks good. The only thing that's here is we do need to evaluate that antiderivative, or find that antiderivative, so 4x over 1 plus x squared. But this one looks so similar to a problem that I've done before that I'm not even going to show the use substitution. If you need to, you can. It's the same thing as 2x over 1 plus x squared's antiderivative times 2. I'm hoping you're okay with it. But this is going to turn into 4x tangent inverse of x. And then this will be minus 2 natural log of 1 plus x squared. And then all plus c. So there's our stuff. So there is our antiderivative. We have wrapped it up and gotten there. It's a lot of work to get there, but we did it. Now I'm going to bring it over to the side and let us begin to finish this problem. Let us begin to finish. I don't know, not my finest word smithing. Wordsmithery? That sounds like fun. Okay, so there is our work. We did the antiderivative. That was the integration by parts problem. Now it's up to us to actually evaluate this guy. So I'm going to go ahead and plug in those that ordered pair. Negative 1. That's important. Negative 1 comma e to the 6th minus 2. When you plug it in, we get on the left side the natural log of e to the 6th minus 2 plus 2, which is just the ln of e to the 6th. And by the way, that's just equal to 6. On the right side, we're going to get negative 4 tangent inverse of negative 1. And then the next one will have minus 2 ln of 2. And then plus c, of course. So there's a lot going on here. We still have a little bit of work to do to get through this. We're going to have 6 equals negative 4. As far as tangent inverse of negative 1, I know that that's equal to negative pi over 4 because of the range restrictions on tangent inverse. And then minus 2 ln of 2 plus c. That's going to turn into, it looks like, pi minus 2 ln of 2 plus c. And finishing all this stuff off, we're going to get 6 plus 2 ln of 2 minus pi equals c. So we have our c value. The only problem is, of course, all of this work is taking up a lot of space. So I'm going to go ahead and do the very unprofessional thing of changing the size of my work. So here we go. We've got all this stuff. Coming back to our original line, we have the natural log of absolute value of y plus 2 is equal to, we've got this massive 4x tangent inverse of x minus 2 ln of 1 plus x squared, and then plus our c. Oh boy! Plus c is going to be plus 6 minus pi plus 2 ln of 2. Okay, so a couple things I want to do here at this point is I'm noticing that there's a lot of issues that might be popping up. So I'm going to try to clean up this work before I go forward. Of course, you might do it differently, but this is going to be one of those times where you've got to kind of check on your own to see if it comes out the same. What I want to note is that I want to deal with the fact I'm about to e to the power both sides. In fact, I'll do it in green here in a second. So when I e to the power both sides, I want it to actually clean something up. I don't want to leave this massive mess as a power because it just looks like it's going to be super nasty. And I wrote the problem so I feel comfortable making this call. What I'm going to do is I'm going to rewrite some of these expressions. First and foremost, here, I'll write it right up. Yeah, I'll write it here. First and foremost, 2 ln of 2 is the same thing as the ln of 4. So I'm going to make a choice right now to rewrite this as the ln of 4, because that way it'll clean itself up. Likewise, I've got this 2 in front of the ln of 1 plus x squared. I'm also going to rewrite that as the ln of 1 plus x squared squared, because that way, again, I'll have e to an ln, and I'll be ready to simplify some stuff. So having done that, that kind of cleans, I think, almost everything up for me. So let me see if I can do this correctly here. Oh, you know what? Technically, I should probably bring up the minus 2. Yeah, I should. Should be a minus 2 coming up. Not the idealist thing in the world, but we'll get there. When I do that and I execute that move, and I just need to draw a line here. So we have a little bit of space to work in. Space, the final frontier. Okay, so now that I have that, on the left side, I'm going to have the absolute value of y plus 2. On the right side, I am going to have e to the 4x tangent inverse of x. Nothing to do about that. On the next one, though, I'm going to have e to the ln, which is going to undo itself or inverse itself away. That'll transform into 1 plus x squared to the negative 2 power. Then we're still going to have e to the 6 minus pi, but we'll also have e to the ln of 4, which is just going to be 4. So having done all that, again, it's not going to get that much better. This is my fault for trying to make this clean up. But basically, we'll get y plus 2 is equal to 4 over 1 plus x squared squared, and then times e to the 4x tangent inverse of x plus 6 minus pi. So wrapping this whole thing up, we've got to do the whole plus or minus thing to get rid of the absolute values. So I will do exactly that. We get plus or minus. Of course, we'll have this minus 2 portion. So we'll end up with y being equal to, I'll write it down where it's bigger. We'll have y being equal to, that just looks terrible. No, that line is so curvy. I'll make it work. Y equals negative 2. We have technically for the moment plus or minus, and it looks like 4 over 1 plus x squared squared e to the, I'm going to rewrite this as 6 minus pi plus 4x tangent inverse of x, just to kind of clean it up. But now remember, recall that we said f of negative 1 has to be equal to something very, very positive. So if we didn't plug in negative 1 correctly this way, what we'd end up with is we'd end up with negative 2 minus another number, which would give us a super big negative number. So in other words, that means that we need to use the plus sign. So with that in mind, we can write out our final answer. Our function is going to be negative 2 plus, and then we can write this pretty nicely, plus 4 over 1 plus x squared squared times e to the 6 minus pi plus 4x tangent inverse of x. And there is probably the most complicated looking final answer in this problem that you could get. I'm realizing I could have just put all that stuff in the numerator, but yeah, we're here. So there is our solution. We've solved our differential equation. It doesn't look so pretty, but if we do plug in negative 1, like if you're looking at this going, there's no way that's right. If you want to check it out, you could plug in negative 1. If you do, you'll get 4 times negative 1, so negative 4 times negative pi over 4, which is minus pi. Right, so minus times minus is positive, so that's plus pi. This will become e to the 6th. You'll have 4 over 1 plus 1 squared, which is 2 squared, or 1. You'll have negative 2 plus e to the 6th. That's exactly what we were looking for. We have accomplished what we were trying for. So again, that doesn't guarantee that we did it correctly, but it does mean that everything seems to check. So I feel pretty confident in what's there, and I don't want to try to tax Wolfram Alpha's computing power by trying to check that answer. So I'll just leave it right there and tell you that I'm very confident in my solution. The final problem, the final chapter of this 7-part integration by parts onslaught of integration, asks you to evaluate a Riemann sum. And your mind's probably like, thanks for that. That's exactly what I wanted. Well, yeah, you're welcome. Because seriously, we'll be fine. So Riemann sums. So the important thing about a Riemann sum. First and foremost, let me just kind of remind you, because I bet this is something that's somewhat rusty. So the typical Riemann sum, I always make that mistake with the n. Our typical Riemann sum is going to feature these ingredients. An f of a plus b minus a over ni. So this Riemann sum features our width and our height. It's a limit of a sum, because basically what you're doing is you're adding up a number of n rectangles, and then you're taking the limit as those rectangles increase in number to infinity, making them infinitesimally small, because as n increases, the width gets smaller. The important thing, though, is not that you know how to evaluate the definite integral itself, like using sum rules or summation properties. It's instead to recognize that it can be transformed into a definite integral. And it's definitely preferable for us to rewrite it as a definite integral, because then we have opportunities to evaluate using the fundamental theorem of calculus, antidifferentiation, all that good stuff. So there's our basic process. We want to try to do the same thing with what's up here. So digging into this expression, first thing I notice is that we have that 2 over n, so that means b minus a over n is going to equal 2. or it means that the spread of the interval, how wide the interval is on which we're working, is going to be 2 units. In addition, inside the function, I see this 2 over ni plus 0. So based on the information found right here, I can see that a is going to equal 0, which means that b is going to have to equal 2. So we now know that our definite integral is going to run across the interval 0 to 2. Finally, it's a matter of us replacing some things. So the last little thing that kind of pops in here is to point out that x is always equal to that b minus a over n plus a, or sorry, b minus a over n I, it's the worst I have ever drawn, plus a. So in there, since that's equal to 2 over ni plus 0, what that means is we can basically replace any of those 2 over ni's with an x. So having done that, we have our width. This will become the dx. Have our x's in place. It is my belief that this Riemann sum transforms into the definite integral running from 0 to 2 of, let's see if I do this right, pi squared x secant squared of pi over 6 x dx. So there is the integral that we're going to be working through in this problem. And it does look like integration by parts. Like, yeah, there's a few more pi squareds than we might expect, but there's a polynomial and a trig function. So having done all that, it's taken a lot of work to get there. We can prepare to evaluate this using LIPET. So as making our choices here between the two, we do have a polynomial and a trig function. So that means we want to let u equal the polynomial. So we'll have pi squared x as our u. Our dv is going to be secant squared of, let's see if I do this right, pi over 6x dx. du is going to be the derivative of that guy, which is going to be pi squared. Technically dx if we want to include it, we probably should. And then v is going to be whatever function has derivative secant squared. Well, that is going to be tangent, but then we have this pi over 6x on the inside. So u substitution, if you wanted to do it that way, or you could just think it through, would give us a scalar of 6 over pi. So that gives us all our ingredient. We're ready to uv minus the integral of v du from here. So let's do it. So uv, taking our move, I'll go ahead and write it up here. What the heck, I'm going to move up to this. I'll just do it from right here. Draw an arrow so that way there's no linkage issues. We're going to have pi squared x times 6 over pi tangent of pi over 6 x. It's going to be so much fun to solve as a definite integral. Can't you hear my enthusiasm? From there, we're going to then have minus the integral of, and we've got a bunch of scalars in front here. So I'm just going to pull out those scalars. Pi squared, it's this piece, by the way. Pi squared times 6 over pi, and it'll be the integral of the tangent of pi over 6 x. So obviously not our ideal problem. It's looking fairly crunchy as far as problems go, although there is some ability to clean it up a little bit since those pi squareds help out a little bit. But from here, the other problem is now we have to deal with the integral of tangent. And that's not necessarily one that you know really well. So as I've done in seemingly almost every problem on this assignment, I'm going to go ahead and do a quick little soliloquy in case you're not sure what the integral of tangent is equal to. And I'm just going to, for the moment, call it the tangent of u, just for simplicity. Like, you'll see why we'll deal with the substitution part. So how do you evaluate the integral of tangent? Well, tangent can be rewritten as the quotient identity, sine of u over cosine of u du. And at that point, you could do a substitution. And if you did your substitution, this is a natural log form, because the derivative of cosine is a multiple of sine. You would end up getting negative natural log of the absolute value of cosine of u plus c. So just as kind of a quick little reminder, like, we do have the ability to evaluate that. Not trivial, but it's there. So given that expression, I'm ready to go ahead and pull it back in. So digging in here a little bit further, again, I'm going to draw another one of those little lines to try to siphon in my work here. Even try to give myself a little more space. Close enough. Okay, so what do we got? We've got what looks like pi x. No, let's put that 6 in front. Let's just make it as good as possible. We'll have 6 pi x, tangent of pi over 6x, Oh, my voice is getting dried out, man. Minus 6 pi. And then for our integral, we have this minus natural log thing. We have this guy over here. It's the end of our little star expression. So if I bring that in, it's going to make this a plus, and it'll be 6 pi the natural log of the absolute value of cosine of u. And sorry, this is the part that I've forgotten to deal with. So we're bringing this in, but we do have to deal with substitution. So we will make that a plus when we bring it back in, but we also have to deal with that pi over 6. That's going to give us a 6 over pi out in front. And then we'll have the natural log of the absolute value of cosine of pi over 6 times x. So I had to bring all that stuff back in, and I was failing to do that. Now once we reach that point, that gives us the opportunity to evaluate this using the fundamental theorem. I'm just going to plug in 2 and 0 first to see if we can get rid of anything. I'm hoping that we can, but we'll find out what happens. So the first term, if we plug in 2, we're going to get 12 pi tangent of pi over 3. It's okay. Plus it looks like 36 natural log of the cosine of pi over 3. So we're going to have a little bit of trig work to do here in a second, but we'll get there. On the next one, so that was the first part of the fundamental theorem. On the second part, we're going to plug in 0, and oh, that's so great. Look, there's a 0 to plug in there. It's just going to be 0 for the first term. Then it will be 36 times the natural log of the cosine of 0. And the interesting thing is the cosine of 0 is 1, and that is 36 times the ln of 1, which is also 0. So really, it just boils down to the first two terms. So we've just got this left. So that gives us 12 pi, and then the tangent of pi over 3. If you need to, feel free to draw a quick little triangle up there in quadrant 1. Pi over 3 is a 60-degree reference angle, so the opposite would be root 3, and the adjacent would be 1. Hypotenuse is 2, but we don't need it for tangent. So that means this first term will be 12 pi root 3. On the next one, we'll have plus 36, and then we have the ln of the cosine of pi over 3. Well, we can use our triangle again. Cosine is adjacent over hypotenuse, which is 1/2. Now after that, we already saw that the second term is gone, so that's just kind of out of the way. We don't need to think about it. And we have a perfectly correct numeric answer at this point. Or at least we should. We'll check it in a moment. But if we wanted to, like, again, I've done some work like this before. There's something about having, what's the word I'm looking for here? There's something about this ln of a fraction that I just don't like. So let me just kind of remind you that the ln, I should put 2 stars, because we already did 1 star. The ln of 1/2 is equal to the ln of 2 to the negative 1 power, which is equal to negative ln of 2. So the only thing that I'm going to do to wrap this up a little bit better is I'm going to write this as 12 pi root 3. Then I'll bring down that negative, bring that negative to the front, so minus 36 ln of 2. So this is the answer that I'm expecting to be correct. Now, in Desmos a few minutes ago, because I found a mistake, I'd made a mistake in my work, I was able to correct it, but I already put in the integral, so I know that the definite integral's value is 40.343. So the question is, did I get the correct algebraic expression here? 12 pi square root of 3 minus 36, 40.343. Yes, I got it this time. Don't have to do it again. So we have once again answered the question correctly. It was just a doozy once more. Like, the fact that I was able to come up with 7 unique looking integration by parts problems that kind of proceeded a little differently each time is one of my better accomplishments. But again, how you spend your time, I can't necessarily tell you. But hopefully if you were looking for integration by parts, extra practice, and maybe even a little bit of a challenge or a wrinkle to throw out there to make sure you really had the topic down, I think this is probably as good a setup as any, particularly at the extra value of getting to review some concepts of calculus A, B, and BC. So having said that, I think I've spent now an hour and a half, 2 hours making this video. So I'm just going to stop and I'll go deal with dinner or play Animal Crossing for a few minutes or something. So having said that, thank you for watching. Hope this has been helpful. But even if it hasn't, have a great night anyway.